Have you learned about matrix multiplication before? If so, did you wonder why are matrices multiplied in such a strange way? In this video, and the related blog post at infinityisreallybig.com, I delve into some of the details about why matrices are multiplied in the strange way that they are. So if this is something that you're learning for the first time, that's going to be good as well. But you will want to know some things ahead of time before reading this section 1.8 of Visual Linear Algebra online on matrix multiplication and composite transformations, really composite linear transformations. In particular, you're going to want to know about linear transformations ahead of time. So I'd recommend going back to section 1.4, learning about linear transformations in 2 dimensions, where we can visualize things very easily. Some very nice visuals like you see here. The key thing to look for there is the idea of what it means for a linear transformation to be operation preserving. That's the key definition of linearity that I'm going to refer to a lot in this video. We go to 3-dimensional linear algebra in section 1.6, including 3-dimensional linear transformations. And in section 1.7, we talk about high-dimensional linear algebra, n-dimensional linear algebra, where n is an arbitrary positive integer. And the key thing to look for here is what it means to multiply a matrix times a vector. You've got an m by n matrix, m rows and n columns, and you've got an n-dimensional vector, column vector, with n entries. A times x will be a linear combination of the columns of A with the corresponding entries of x as the weights. Okay, so go back and review that if you need to. That comes into play in this section. This section is pretty technical. Okay, and I don't want to go through all the technical parts. I want to really, besides talking about big ideas and some subtle details, I really want to get to the heart of what A times B is and why we multiply matrices in the way that we do. The visuals that you see here don't come until the very end, until the examples at the very end. So if you want to understand these visuals, make sure you hang on until then. Okay, but you're going to want to, as you work through this section, have pencil and paper handy, calculator handy to double check things. Make sure you understand what's going on. It's very technical. So at the beginning of the section, I first just start talking about function composition in general, not necessarily of linear transformations. And the first thing I emphasize that's something called a binary operation, and we're going to see the circle operator in here that emphasizes that it's a binary operation, where you take 2 things and combine them to get a new thing. Just like with addition and multiplication of numbers. When you multiply 2 numbers, you're combining the 2 numbers to get a new number. That's an example of a binary operation. With function composition, you are plugging one function into another. And I talk about an application here. You should realize that this application is not super realistic. You got a snowball that's melting, okay? First thing I do is I assume the snowball stays a sphere as it melts. That's not realistic. Second thing that I do is I assume that the volume is a linear function of time here, 100 minus 10t, as t goes from 0 to 10. T is the number of hours since it started melting. 2 unrealistic assumptions just for the sake of illustration, okay? The question we want to answer is, how does the radius of the snowball depend on time? We know how the volume depends on time, and we know how the volume depends on the radius with this famous formula right here, right? V equals 4/3 pi r cubed for a sphere. Well, we can solve that equation for r as a function of v by doing a little bit of arithmetic and doing a cube root to get this formula here. So r depends on v, and v depends on t. Therefore, r does depend on t. Just plug this function into this function. And that's what composition is, plugging one function into another to get a new function that I'm calling h of t. Okay? This would be how the radius of the snowball depends on time. There's an inner function f, there's an outer function g. The inner function gets done first, the outer function gets done second. If you've taken calculus and you know about the chain rule, you know that's really important for taking the derivative of this function. Here's just a little way this can be visualized. That's going to be important later. The domain of the inner function, I'm taking to be the interval from 0 to 10, because that's the domain for the application. Its codomain is the real number system. Its outputs are real numbers. That's the domain of G and the codomain of G as well. And then for the composition, G compose F, where you do F first, then G, takes this domain to this codomain. Okay? Again, that's going to be helpful for some examples later on. Here's where I talk about the circle notation. H equals G circle F, or GOF as it's sometimes called, is G of F of t, just like I talked about before. You could do it the other way around in general. you could form F circle G of G, or fog, okay? However, in general, they're not going to be the same function. In this application, with the snowball melting, it really doesn't make sense to do the opposite function. However, symbolically, there's nothing stopping me from doing it. However, if I did, I do get a different formula. And the key thing is not just the fact that the V and the T are different letters. That's not the key thing to focus on here. The key thing is these are different formulas. These are different functions. For any given input, you're typically going to get a different output. The arithmetic operations are different. If you gave the independent variable in each case the same name, like x or something, and you graph both functions, you get different graphs. So function composition is not commutative. And you get a different kind of function. But what happens when you compose linear functions from pre-calculus and calculus? Linear meaning their graphs are straight lines. They have a slope and a y-intercept. You could say one of the functions has formula ax plus b and the other one has formula cx plus d. What do you get when you compose them? Well, you still do get linear functions in that sense. Got a slope and intercept. The slopes are the same, but the intercepts are different. Even for these functions, f circle g does not in general equal g circle f. However, what about according to our new definition of linearity? The operation preserving property that I was alluding to, that you can look up in section 1.4 and also section 1.7. What happens with linear transformations? Okay, with linear transformations, you really don't want any extra constants that get added. Okay, you're going to see that with an example here in a minute. So I'm going to assume the general case T is going from n-dimensional space to m-dimensional space, and S is going from m-dimensional space to l-dimensional space. We can therefore form the composition S circle T, or SOT, I guess in this case. Is it linear? Is it a linear transformation? Is it operation preserving? Here's the key calculation here. A and B are real numbers, scalars. U and V are vectors. I want to see, is the function applied to a linear combination, AU plus BV in this case, equal to the corresponding linear combination of the function applied to the vectors? That's kind of a mouthful. The function S circle T of AU plus BV, does it equal A times S circle T of U plus B times S circle T of V? It does, and this calculation confirms it. I always used to look at these kind of calculations and be pretty confused. Like, what world is going on here? It's not as hard as it looks. Take it step by step. What's this first equality from? That's just the definition of composition. S circle T of an input is S of T of that input. Okay? What about this equality here? That's using the operation preserving property of T. T being linear. T of this linear combination, AU plus BV, is the corresponding linear combination of T of U and T of V, meaning take the same scalars and put the plus sign there with the T of U here and the T of V there. It's kind of like you're almost distributing the T through and then factoring out the A and the B. Okay, that's not literally what's going on, but it's analogous to that symbolic at a purely symbolic level. This equality uses the fact that S is linear. We have S of a linear combination of two vectors, and the vectors are being multiplied by scalars. S is linear, so it's also operation preserving. You get the same analogous linear combination, A times S of this vector T of U, plus B times S of T of V. And the last equality there is the same as the first. It's just definition of composition. That's verifying linearity. Okay? Before we get into the main content now, this is all prelude, we should re-emphasize what I said at the beginning. If A is an n by n matrix and X is an n-dimensional vector, an n by 1 matrix, a column vector, we can form the matrix vector product. We've talked about that before. AX will be the m-dimensional vector formed as a linear combination of the columns of A with the entries of the vector X as the corresponding weights. In a formula, if these are the columns of capital A and these are the entries of boldface X, this is the formula. Linear combination. Columns of capital A are these vectors boldface A1, boldface A2 through boldface AN. With the entries of boldface X, these unbold-faced x's as the weights in front of the vectors. You can write that with sigma notation as well. Okay. What comes next, I mostly want to skip over because I want to get to the main definition. However, you should not skip over it in reading. I consider some low-dimensional examples, symbolically, without numbers, without specific numbers, I should say. This example, T goes from R to R, S goes from R to R, so the composition also goes from R to R. And the main point to emphasize is the matrix that represents the function composition is really a 1-by-1 matrix, which is really a number. And it's the product of the two numbers A and B that represent each of these transformations individually, that are the slopes if you graph them. This is the punchline here. Matrix multiplication is easy when the matrices are 1-by-1, in other words, just numbers, multiply the numbers. This notation is just emphasizing I can think of the numbers as being matrices. Second example is like this. T goes from R to R2, S goes from R2 to R. Here's the key thing we want. We want to define A times B so that this equation is true for all x in R. And the composition goes from R to R. The product of A and B has to be a 1-by-1 matrix if that's going to work. Okay, so here's the part I'm skipping over. This stuff is based on just what capital A and capital B have to be. And we've talked about these formulas before. This is the composition down here. I just calculate this by taking the formula for T of x right there and plugging it into S right there and do this multiplication. The answer is a number, a 1-by-1 matrix. The product of A and B is therefore going to have to be that 1-by-1 matrix, that number. Okay, and this is something we've really done before. This answer really is a linear combination of the columns of A with the entries of this vector as the weights. This is a 2-by-1 matrix, which is the same as a two-dimensional vector. Okay, and then it gets a little harder here, but again, here's the key. T goes from R2 to R, S goes from R to R2, the composition goes from R2 to R2. Its matrix has got to be 2-by-2. This section really involves some new ideas. Here's some formulas you should double check. Here's the final calculation that involves a linear combination of some vectors that can be interpreted as a matrix times a vector as before. So the product of these two matrices, A and B, better be this matrix. Again, this is a new way to think of this because this is not really a linear combinations of the columns of A with the entries of this as the weights. Not in the same kind of way, at least. Think of this matrix as consisting of two columns, which are a 2-by-1 matrix times a 1-by-1 matrix. You can think of it that way. And this pattern is going to work in general, including in this situation here, which is our most complicated situation before the general case. We're almost in the general case here. Hang on. T goes from R2 to R2, so does S. The composition, therefore, goes from R2 to R2. We want this equation to be true. A times B has got to be 2-by-2. This is the hardest calculation here. So I've got general matrices here, general calculations involving linear combinations of columns with entries of a vector as a weights. Then I'm plugging one function into the other and getting some complicated looking things. You should double check these calculations. There, at the end, we ultimately can say it's a linear combination of a couple column vectors, so it can be thought of as this product. So we want A times B to be this matrix here. Okay. And we follow the same pattern before. If we follow the same pattern as before, right here, we see that we do get the same, what we want to get. Okay. A times B1 is this, A times B2 is this. Combine those two things in a matrix like this. That is what we want to get. Now we're on to the general case. So now we're going to go a little slower. Okay. The general case is actually a bit more interesting and even enlightening once you get it. Okay, the hard part is getting it at first. It takes intense concentration to fully understand. And by the way, again, hang on for the visuals that come in the examples. There are going to be some visuals to come. T goes from Rn to Rm, and S goes from Rm to RL. As you go through this, you may want to, on your piece of paper, write something like I've written on here. See this piece of paper? You might want to write this stuff just so you don't have to scroll up and down so much. Okay, so you can see it there in front of you. Maybe pause the video and write down what I have there. Let's take it carefully. T is going to have a m by n matrix B representative. Notice T goes, maybe you've noticed this pattern already. T goes from n to m, Rn to n-dimensional space to m-dimensional space. So its matrix has got to switch around the m and the n. It's got to be m by n. M rows, n columns. Matrix for S does something similar. S goes from m-dimensional space to l-dimensional space. Its matrix has to be L by m. L rows, m columns. We once again seek to define the product A times B so that this is true. That's the key. That's what this is all about, okay? That's the purpose of why we multiply matrices in this strange way, is so this equation works, okay? That's what I was referring to at the beginning of the video. So take it carefully. Suppose these are the columns of capital B. Now remember, B was, I gotta look at my notes, B was m by n. M rows, n columns. These are n columns, where each of these vectors is m-dimensional. X is what you're going to multiply B by, B times X. It's got to be n-dimensional as well. Well, these are m-dimensional, this is n-dimensional. We already know that B times X is a linear combination of the columns of capital B with the entries of X as the weights. That's what this is. Here's a key. Since S is linear and S of y equals A times Y, we can also say by linear operation preserving property of A in this case that this equation is true. B times X is this, first of all, and then that's essentially S of this. So it's operation preserving. You get the same corresponding linear combination, S of B1, S of B2 with S of Bn, which can be done by A times B1 and A times B2 and A times Bn. And that, hey, that's a linear combination of some column vectors. This is a linear combination of L-dimensional vectors, n L-dimensional vectors with the entries of X as the weights. That's a matrix times a vector. It's this matrix times this vector. If this is to equal AB times X, we should define A times B to be this matrix. That's what we do, okay? So we want something to happen. So we define it to happen. It's not a theorem, it's a definition. We're not proving this, we're saying this makes sense, so let's define it this way. Now there is an alternative approach to matrix multiplication involving dot products. And this is actually the way that I learned matrix multiplication at first. And this is even more mysterious. This one has some motivation behind it. Again, wanting this equation to be true here. Wanting that fact to be true. That's the key. So that's the motivation for it. This approach is like it's pulled out of a hat, it seems like, if you learn it this way. So what are the benefits of talking about it? Well, first of all, the main benefit is that it's a faster way to compute A times B. Okay, if you've got two matrices you can multiply, this is a faster way to go. So that's the main benefit, I guess I would say. And you will see it written in books, so it's worth talking about. I don't want to go through all the details here. Let me just point out that the main equation is down here. Cij is supposed to represent the number in the ith row and jth column of the answer. If capital C is capital A times capital B. Notice it's a sum of products, just like dot products are. And in fact, it is a dot product. Okay? You got A over here times B to get an answer. To find the answer, the number in the ith row and jth column, take the ith row of A and the jth column of B, think of them both as vectors, and dot them. Okay, now we've typically only thought of vectors as being column vectors so far, but you can certainly think of vectors as being row vectors as well. Okay, they're both, looks like m-dimensional vectors in this case, yeah. This is a dot product. It's the dot product of the jth column of B with the ith row of A. And again, that row could be thought of as a vector. It's a quicker way to find A times B, but it's less meaningful as a definition. Before we look at the examples, which do get visual, except the first example. The first example is calculational. We should emphasize one final point here. To multiply A times B, A is L by M, it's on the left, B is M by N on the right. The number of columns of A has to equal the number of rows of B. And the answer is going to have a dimension L by N. Same as the number of rows of A and the number of columns of B. Yeah, L by N. The final answer has the same number of rows of A and the same number of columns of B. Because of this, you should also realize that just because you can do A times B does not mean you can do B times A. In fact, it's only going to work if L and N are equal. However, in that case, A times B does not necessarily equal B times A. That's reflecting the fact that function composition is not commutative. All right, take a breath. Here's the examples. There's going to be 3 examples. First one is high dimensional and computational. Second and third examples are low dimensional and visual, and that's the end of the section. All examples worth considering here. I don't want to check all the calculations here, but we should emphasize maybe some dimensional things. T goes from R5 to R3, so its matrix is 3 by 5. S goes from R3 to R4, so its matrix is 4 by 3. Here is our product by the definition. That makes more intuitive sense in terms of wanting the function composition to match the product. Now, doing it that way, finding A times B in that way is a pain. And I only do one example, and the other 4 columns here are for you to check. So here I calculate A times B1, in other words, this matrix times the first column of B. It's a linear combination of the columns of A, here they are, with the entries of B as the weights, the 1, the 2, the -3. And at the end you get this 4-dimensional vector, etc. Here's the final answer. You can see this is the same as the first column of the answer. You calculate columns 2, 3, 4, and 5 now. Okay, again, here are A and B up here. And here's the answer down there. I do confirm the dot product approach works as well. For example, C32, and by the way, you should say C32 rather than C32, is the number in the third row and second column, -18 right there. That's the same as the dot product of the third row of A with the second column of B. Okay, -18. Formula for the composite is this. And now you can do things like find the null space. The kernel of the linear transformation, also called the null space of the matrix. You can do row operations like I talk about in section 1.7. I don't do the details here. I just say RREF to say do the row operations to reduced row echelon form to get this. A couple free variables are x4 and x5. The kernel of the transformation, which is the null space of the matrix, is this. And there's a typo here that I need to fix after I mix the video. This should be the kernel of S composed T, not T itself, which is the null space of A times B, not the null space of A itself. I need to make that change here, so you will see the change when you go to the blog. All right, final 2 examples. The fun examples are visual. It is worth reviewing section 1.4 though, so you understand the meaning of these visualizations. I'm not going to talk about the meaning a ton. The linear transformations in this example I'm calling S and R, not S and T. Why? Because S represents a shear and R represents a rotation. I want the letter to represent the name of the transformation. Shears, remember, well, this particular shear takes vectors above the horizontal axis and slants them this way, and vectors below the horizontal axis and slants them this way. And this rotation is a rotation counterclockwise by 90 degrees. Both compositions can be formed, by the way. These matrices are square, 2 by 2. The number of rows equals the number of columns, and you can compose R compose S and S compose R to get 2 different answers, and we'll see that we get 2 different functions. Here they are. I am using different letters for the variable inputs. I didn't have to do that, but just to distinguish the formulas a little bit. But the key thing is the operations are different. Here, for example, in the first component, we're subtracting the original first components. Here, you're just taking the negative of the second one. So they are different formulas. You can just double check these with the dot product definition. And here we are onto visualizing these things. Here's our first visual. So on the left, you've got R, circle S, meaning shear first, then rotate. Remember, you work from right to left with the circle notation. The red butterfly curve is the original set. The blue one at the end right now is the image in both cases. The stuff in between is just to help you see the shearing and the rotating. So again, on the left, you shear first, then rotate. On the right, you rotate first, then shear. And you get different final images. These are different functions. You're going to get different images. These formulas are different, okay? Like, even if you use the same letters. It's not commutative. We can visualize these things as vector fields, which would be different vector fields too. Technically speaking, vector fields are static objects like this. How do you make these graphs without a computer? Well, it would be a big pain, but you take it point by point. For any given point, you plug the point into the function and find the answer and treat the answer as a vector. I'm writing the inputs as points and the outputs as points, but think of the inputs as points and the outputs as vectors. I could have written this as a column if I wanted to, but it was taking up too much space. So, for example, the point 1, 1, when I plug those coordinates into this formula, I get -1, 2. And this vector right here has components -1, 2. Horizontal component -1, vertical component 2. Over here, 1, 1 gives you 1 minus 1 is 0, comma 1. This vector has component 0, 1. It's got a 0 horizontal component, it's vertical, and second component equal to +1. It goes up by 1. And you can check other vectors here as well. This can be animated as well. If we animate from the identity vector field, in both cases, I of x equals x, where the input equals the output, but you think of the input as a point and the output as a vector. The red pictures here are the identity vector fields, and in both cases the blue pictures are the final vector fields. Again, on the left we shear first then rotate. On the right you rotate first then shear, and you get different vector fields in the end. And again, the intermediate stuff is just to help you visualize what's going on. Final example involves composing two reflections, RH and RD. RH is a reflection across the horizontal axis. RD is a reflection across the diagonal 45-degree line through the origin. These are their matrices, capital D for diagonal reflection, capital H for horizontal reflection. You can think about those. You do these compositions in the opposite order, you get different formulas, ignoring the fact that I changed the letters. Once again, you can visual. On the left, it's reflection across the horizontal first, right now, and then the diagonal. On the right, it's across the diagonal first, right now, and then across the horizontal. Get different final blue images in the end. Though they are related, they are 180-degree rotations of each other, and that's reflecting the fact that this formula is true with this example. Here are the final vector fields, and then here are the animations of those vector fields from the identity vector field. Be careful how you interpret this. For example, the one on the left, we're not reflecting literally across the horizontal axis with each vector, because we need to keep the base point the same as we go. Instead, imagine at each point little horizontal lines that kind of represent a horizontal axis at that point. And we're reflecting across those little horizontal lines. And then at each point, we're imagining a little diagonal line at a 45-degree angle. And then with that diagonal reflection, you're reflecting across those little lines in each case. For the one on the right, you do it across the diagonal first, like right now, and then across the horizontal. And again, you get different answers in the end. So I hope wading through all the details made it worth it here at the end to see these visuals, because I think these visuals are really cool, and I hope that you got a lot out of this. Thanks.